Okay, so in this video, I want to dive a little deeper into the idea of enthalpies of reaction and specifically kind of the ratio of heat that goes with a reaction. So just to kind of get us started, let's look at this example of water splitting, right, where we take liquid water, H2O, and we turn that into hydrogen gas and oxygen gas. Now, the thermochemical equation is on the slides here, where 2 moles of H2O produce 2 moles of H2 gas and 1 mole of O2 gas. Along with that, the enthalpy of reaction is positive 572 kilojoules per mole. So right, looking at this equation here, right, do we think that this is an endothermic or exothermic reaction? Right, so this is an endothermic reaction, very good. We know that from the positive delta H value, right, endothermic reactions that are adding heat in, right, heat is entering the system, those are going to have a positive delta H. Now, as sort of a follow-up, right, what if I were to flip this reaction around, kind of make the reverse equation, where I have 2 moles of H2 gas plus 1 mole of O2 gas, producing 2 moles of H2O in the liquid phase? And so kind of flipping this reaction around, right, do you think that the reversed reaction will be an endothermic or an exothermic reaction? Yes, so this is an exothermic reaction. You can kind of imagine, right, that if in the original equation, right, where it was endothermic, heat was like a reactant, right, when I flip the products and the reactants, I'm basically flipping where the heat is as well. So, right, not only is water being produced in this reversed reaction, but also heat is being produced there with it. And so whenever heat is produced, right, that's exothermic. So right, we know then that delta H should be a negative value. Along with that though, and this is what's really neat here, is that the size of delta H, right, the magnitude of it, is going to be the same between these two equations. Right, so basically if we flip the products and the reactants, if we reverse a reaction around, the resulting enthalpy of reaction is going to flip in its sign, but its size stays the same. So right, in this video, we're going to cover what we call like manipulating reactions, kind of twisting and turning different chemical equations, and then predicting like what enthalpy change will go with them. Right, so in this scenario, because I reversed the reaction, I'm going to reverse the sign of my delta H. Now let's imagine kind of another way that we can manipulate enthalpies. So again, looking at our water splitting example, what if instead I were to like simplify this reaction and use fractions for molar coefficients, right? So usually in class, I will try to use just whole number coefficients because I don't really like to see the fractions in my molar coefficients, but technically like a 1/2 is acceptable, right? In certain scenarios, actually the fractions are kind of preferred here. But so, right, my simplified equation reads as so. I have 1 mole of H2O producing 1 mole of H2 and a 1/2 mole of O2. And so for this equation, right, what do we think the enthalpy change will be for this now simplified reaction? So what is delta H in this scenario? All right, so hopefully you're thinking like proportionally here, right? And what exactly delta H means in terms of per mole, right? For this halved reaction, the enthalpy change is also halved as a result, right? So for our, right, so our second reaction here actually has an enthalpy change of positive 286 kilojoules per mole, whereas the doubled version had positive 572 kilojoules per mole. This doesn't actually like really change, say, our mole ratios of enthalpy to moles of different substances, because like, let's say from the top reaction, I say 572 kilojoules, that's per 2 moles of H2O reacting. From the bottom reaction, right, I would say like for 286 kilojoules, that's per 1 mole of H2O reacting. It's really the same thing, right? That proportionality stays the same. And so kind of the rule of thumb here is that if you are to like multiply or divide a reaction by a factor, so I mean like multiply or divide all of the molar coefficients in a chemical reaction, then you're also going to multiply or divide the delta H that goes with it by that factor, right? So in this example, it's like I took my first reaction and I divided it by 2. As a result, I'm going to then divide the enthalpy of reaction by 2. This works in the other direction as well, right? If I were to double my reaction, then I would double the enthalpy that goes with that. So right, just to kind of like quickly summarize those things here, right, let's look at this example of nitrogen gas and hydrogen gas forming ammonia or NH3. Its thermochemical equation is written up above, where 1 mole of N2 plus 3 moles of H2 produces 2 moles of NH3 and has an enthalpy of reaction of negative 91.8 kilojoules per mole. And so what we just saw in the previous slides was that if we are to reverse this chemical equation, then our resulting delta H is going to flip in sign. So right, my reversed equation reads as 2 moles of NH3 producing 1 mole of N2 and 3 moles of H2. That has a delta H reaction of positive 91.8 kilojoules per mole. Additionally, if I were to, say, multiply this entire chemical equation by some factor, even if that factor is like a fraction, basically dividing that equation, then my delta H value also needs to be multiplied by that same number. So, right, if I were to double the entire original equation, make it 2 moles of N2 plus 6 moles of H2, producing 4 moles of NH3, then my enthalpy of reaction would be negative 184 kilojoules per mole, right? Just double what I had before. But so, right, this is really just to kind of introduce the idea of manipulating different reactions and manipulating their enthalpies with them. We'll see more applications of this in our next class period, but please let me know if you have any questions, and I'm always happy to help. Bye.